Alrighty. How's everyone's hangovers? Who's ready for some low-level intrinsic programming and that kind of thing? All right, let's go. So here's what we're going to do. We're going to take one of the most useful constructs essential to pretty much all of programming and not use it, because why not? Essentially, the scope of this talk is a single program, multiple data approach to writing oscillators. If you're familiar with GPUs and with shader language, for example, that's a domain-specific language for writing this sort of very highly parallel code. We'll get to the rationale for that in a bit. So, I mean, I think a reasonable question at the outset is, well, why not use a domain-specific language for that? For example, C major. Again, you could, but I'm not going to. I enjoy the idiomatic nature of C++, the fact that you can combine different idioms and not have to keep track of multiple languages. So we're going to use C++ and some intrinsics. So branches, well, what are branches? We haven't got too much of the student crowd in today, so hopefully I don't have to explain that in too much detail. It's simply branches in flow control in your program. So that's if statements, that's switch, for, do, while. A lot of these sort of common operators tend to result in branches in control flow, and we're going to try and avoid that. Now, something we have to just keep in mind while we're doing all of this is C++, it's not truly a virtual machine, but as a language standard, the observable behavior, what you see your code do and in what order it does it, is well defined, it's standardized, but the compiler can deliver that result however it wants. We are trying to write very high performance code here. We are somewhat dependent on the compiler's decisions, so it is going to be a little bit fragile. We are reliant on the compiler to kind of be nice, but at the same time, we do have some tools to kind of keep tabs on that. I think when compilers at O2 or O3, they're optimizing. They are trying to make their best effort and making a lot of trade-offs to try and make your code go faster. We can help them do that by giving them more surface area to work with. That's one of the kind of focuses of my work here. Equally, though, sometimes the compilers think they are helping and they can do something quite counterproductive. If anyone from Apple is here, come and talk to me afterwards. So what's going on here? So we've got some C++ code here, or it's pretty much just C actually, for a naive oscillator. So this is just a sort of phase increment and wraparound sawtooth oscillator. And on the other side here, we've got the assembly code that is compiled to. I've been using Compiler Explorer a lot, godbolt.org. Really fantastic tool. If you haven't used it, I really recommend checking that out because it lets you write C++ code, or I think it supports a few other languages as well now, and then try it in different compilers, different optimization settings, and see what code it actually generates. And so this obviously is assembler rather than machine code, but it's essentially just a text representation of more or less the same thing, which executes on what I refer to as machine language VM, which is kind of the processor. So if you look at the disassembly view in the debugger, I think there's a misperception, maybe at least with more junior devs, that what they're seeing there, this sort of thing, is what's actually going on in the hardware. And it's lower level than what you see in C++, but this is really not what's going on in the hardware. There's a lot of stuff at lower level that you can't see that happens between the level of the machine instructions and the actual transistors, and this is these things. It's instruction fetching, execution, the sort of address space remappings of virtual memory, the state of the caches, branch prediction, the loading, storing of instructions and data. And in this sort of slightly shadowy world between what we can see and what the hardware is actually doing is where a lot of these nasty sort of hardware security bugs have happened in the last few years. So security researchers have been essentially exploiting the gap between what you see happening here in the code and what's actually going on in the hardware, and basically getting the process to leak secrets and give away information it shouldn't be giving away. Anyway, why do we want to be branchless? Well, let's think about what's in a modern CPU right now, and this is the M1, which I'll just use as the sort of case study for this. But pretty much all sort of desktop, laptop, and the kind of A class, the larger ARM cores, they're all converging on essentially the same set of evolutionary constraints. So they all have broadly, if not the same, then similar feature set. So it's an octa or deca-core superscalar CPU with 14 wide dispatch and 128-bit SIMD, which is the vector units. There's three main kinds of parallelism that this implements. You've got thread level, and then instruction and data level. Thread level we are not looking at today. Why not? So I'm going to say something slightly controversial here. You can throw it back at me in the questions, but I believe that plugins should only use thread level parallelism for their processing as an absolute last resort. Why? Well, because the host is already using it. The host is running a whole lot of plugins. It's trying to load balance those across the available cores, across the available CPU resources. And I believe that as far as possible, plugins should just let the host get on with that. I know Clap does have some APIs to make that stuff work a bit better. I haven't delved into that yet. Other thing with the thread level parallelism is basically it's good at big chunks of work. 100 microseconds doesn't sound very big, but that is a long time in CPU time. These CPUs are running sometimes more than one instruction per clock, sometimes as many as 10 or 12. So at 3 or 4 gigahertz, they're easily crunching through 1 million instructions in that time. If you can't write a decent plugin with 1 million instructions, what are you even doing? And then the data, some of the data synchronization stuff is quite expensive, moving blocks of data back and forth between caches and cores. And you've got obviously the challenges of thread synchronization there. So gonna skip over that. And I'm also just going to say we're not looking at symmetric multi-threading where you have 2 threads share a core, and not looking at in-lane vectorization. Essentially, with these sort of different levels of parallelism, you pretty much want to use them in one place, because if you've already kind of exploited all the width available at one level and you try and do the same thing at another level, it's not going to be available to you. So what's actually in one of these CPUs? So this is all the inside of one core. So there are 8 of these on an M1, and it's broadly organized, as are all modern CPUs, into a front end which organizes stuff, fetches data, decodes instructions, gets them ready for execution, and the back end which does the actual work, all the maths, the logic, and it's got the vector units in there. CPU is reading through our machine instruction stream and making a best effort to get everything done as efficiently as possible. But again, as with the compiler, we can help it along by giving it more surface area to work with. So let's zoom in on the bit we're actually sort of interested in on this CPU. So I imagine most of you will be familiar with sort of the basics of SIMD vector programming, where you're working with registers that contain, typically sort of 4 or 8 single precision floats. So on this one, it's 128 bits. You get 4 float 32s in there. But there's actually four of these units on this chip, each of which can tick once per CPU clock, which is to say every cycle of the CPU, you can potentially send 4 vector instructions each four lanes wide. So in theory, 16 floats for every clock tick. And there's more to this because although you can send these every clock tick, they don't return a result straight away. So here we are multiplying 2 numbers together and then subtracting one of them from another number. So these are both they look like they're single cycle instructions. They only take one instruction to dispatch, or one cycle to dispatch, but they don't return the result straight away. So this is sometimes called instruction latency. It's, we talk about latency a lot in this business. It's not these ones. So it's not audio latency. It's not filter unit sample delay. This is on a much smaller scale, sort of sub nanosecond scale. And some of these more complex math operations, if they are implemented in hardware with a machine instruction, they can take a lot longer. So whereas a multiply might give you a result back after 3 or 4 cycles, if you do a divide, that can take a lot longer. Some of the older processors would actually sort of dispatch a separate software routine to do divides. These days, they mostly have a hardware divider, and it will usually work in maybe 10 or 20 cycles, but it varies a lot from one processor model to the next. This is sort of an active area that they are working on improving. So how can we keep our CPU busy when we've asked it to do a multiply and we need to wait a couple of cycles for the result? Well, I sort of sometimes like to have a mental model of the CPU as being a slower and wider machine. You can see effectively here there's 3 streams, each 4 lanes wide, and if we've got one set of instructions that we are running at t equals 0, that's not going to be ready till t equals 3, but then if we can queue some other stuff up, that can go on the next tick, and then the next one in the next tick after that. So in effect, you can have 48 data streams, so that's 12 streams that are each 4 lanes wide, and it's a sort of imaginary single cycle latency because basically you're never actually wasting time waiting for the result, but effectively a slower clock rate. But the end result we're looking for is to get much higher throughput. The CPU will try and do some of this for you, but again, if we can give it more to work with, then it can hopefully do an even better job and get higher efficiency. But eventually, we do run into some limits, and this is just that CPUs have a register file. Those of you who ever had to program the original 32-bit x86, you only had 8 registers. I think on some of the home computers, they only had something like 3 that you could actually use. But this does become a limiting factor because effectively, as your instruction stream gets wider, you're sharing out sort of fewer registers per stream. And once you get to something like 12 wide, which would be the optimum for throughput, you've only got 2.5 per stream, which is less than ideal. And you get these sort of spills and refills, which we'll look at in a bit. Just to also say, even on the same CPU, you can, or the same chip, you can have different core architectures now. So if you've come across sort of big. LITTLE on ARM or performance and efficiency, they can have some sort of quite different characteristics, and the ideal sort of instruction sequence might vary from core to core, even on the same device. They will give you a consistent result in terms of the numbers. That is guaranteed. But in terms of the performance and in terms of how efficiently it will do that, that can vary. So that's something to watch out for. So yeah, before we jump in and look at the actual kind of tech underpinning this, basically you've got to make sure it's actually working, that it's actually running efficiently. Evaluate all the time. Using profiler tools and using micro benchmarks, using Compiler Explorer. So that just kind of keeps an eye and makes sure it's actually doing what you think it's doing. So these are some of the techniques, and I'm going to kind of cover those first so that we can then just look at the oscillators as they're actually sort of built. We've got SIMD intrinsics, which is essentially a way of writing kind of SIMD assembler instructions from C or C++. We'll be using data interleaving, and this is all wrapped up to be kind of reasonably transparent to the programmer. And then there are these sort of 3 branch-free techniques for doing useful maths and control flow, which I'm covering in a bit more detail. So there is still one branch in this code. We are branching at the end of the inner loop. So basically, your sample counter that's ticking over. When you get to the end of the process loop, it is going to do a branch just to say, are there still more samples to process? You can unroll that, and you can get compilers. You can tell the compiler, I want to unroll this 4 times or 8 times, but it just starts to make the code a lot bigger, which then hurts your instruction cache, and sometimes it won't actually gain you that much efficiency anyway, because we've already kind of squeezed most of the juice out of the lemon at that point. So the intrinsics wrapper, the objective here, I'm sorry it's a little bit difficult to read on this screen. We want to be able to write clean and readable code, which hopefully this is. We want there to be no performance penalty versus just using raw intrinsics or even hand coding in ASM. There'll be maybe, you could probably get it to be a bit more efficient if you really hand coded, but that's going to be really efficient on one target. You're probably having to address potentially dozens of targets, and most of us, unless you're working on a game engine or something like that, you're just not going to have the resources to write optimal code paths for 20 different architectures. So this is sort of trying to get 95% of the way there for a lot less effort, so that you can generate different layouts and actually then micro benchmark them to see whether they're optimal. And obviously, it also hides the different instruction set architectures, so things like Neon or SSE, AVX. There's some limits on this, so we do have some limitations to deal with. We don't have all the control flow statements that we are used to being able to write. So if and else, we can't do that. Any relational, so C++ requires that the relational compare operators evaluate to bool, which turns out to be annoying for what we're trying to do. I'll get onto that. The conditional ternary operator can't be overloaded, which is also annoying. So we have to write some functions for some of those things. So we have to have basically like a compare method instead of the greater than sign. And then we have to import those. It's a C++ language restriction around dependent names that you kind of have to bring those into scope with the using declaration. So there's a little bit of annoying boilerplate, and also a little bit of overhead when you're moving between so array of structures and structure of arrays, the 2 different data layouts in memory. Essentially, there is a bit of overhead there, but try and do that outside of the inner loop, so we don't pay a penalty for really doing that. I'm not going to dwell in a lot of depth on how this intrinsics wrapper is actually built, because Something similar is in development as a language standard, standard experimental right now, SIMD, which will abstract a lot of this stuff. So then it's really more about what you can do with it rather than what the underlying implementation is. I think that may be in C++ 26, but I don't know yet. So this the wrapper here, you can see the sort of things it does. We're basically passing it a width. So this is sort of an example implementation using some neon. These are ARM neon intrinsics here. So you'd need a different version of this class for the Intel architecture for AVX or SSE. We are passing an interleaving size as a template parameter, so that's a compile time constant. And so the idea is that these for loops can just be fully unrolled by the compiler. There's no need for branches there. It's just going to essentially copy and paste and like blat those instructions in line. We can have implicit conversions from floats, so we can just assign a constant to one of these things. You know, in effect, you've got a variable that's maybe 4, 8, 16, 32, etc. Lanes wide, and we can just set that to a float value, useful if you're doing like a comparison or something. And we do rely on the compiler to kind of deduplicate some of those. I mean, generally, this is all requiring a bit of cooperation from the compiler, which unfortunately can't always be relied upon. So as I say, use Compiler Explorer, or if you're using Clang, there's -s, which gives you a disassembly. So this is kind of one of the core tricks, really. Over on the far side there, we've got simple control flow setup. If A greater than B, X is C, else it's D. And we need to borrow a little trick from quantum physics here, and basically go down two paths at once until we know what we want. And so the way this works is we have a comparison instruction that generates a logical mask. So it's basically generating bit fields of ones or bit fields of zeros, and then we can do an and not on that to basically combine the two paths and then sum them together, either with a bitwise, or we can use a floating point add, because anything that's all zeros is obviously going to be zero. They are more or less equivalent at that point. So you can use that for picking different values for different lanes depending on those conditions. So you can see here we're testing whether A is greater than B, and for these ones it's going to set those bit fields to 1, and for those it's going to set it to 0. And so it's picking between those C and D results here based on the result of that masking operation. Some instruction sets will give you can build things like max and min and clipping functions with that, but sometimes that's available directly in intrinsics. Clipping and scaling to produce window functions. So we've already got max and clipping, and then basically we can just scale some truncated ranges to produce a window function, and you can do that across multiple lanes in just four instructions. So you know it's an absolute. A max and then a subtract and a multiply, and that gives you a sort of 0, 1, or in this case 0, -1 ranged window function that you can then use for other things like generating polynomials. So polynomials are going to be key to this. They are really, really efficient for this type of architecture. We don't want to use lookup tables. They don't parallelize well. They are very memory intensive. It kind of hammers the cache a bit, and if you miss L1, then the L2 cache can be actually pretty slow to access, particularly as you can't really, each lane is going to have a different value. It's going to be a different position in the lookup table. So typically that will require sort of a unique memory access for each lane that can end up being pretty inefficient. Using the sort of transcendental math functions in the standard library. I mean, there may be some compilers that are optimizing this down to the level of intrinsics, but typically that doesn't seem to be the case. I think some of the sort of hardware implementations of these are less numerically accurate than the IEEE standard would require. And so these, again, can be very expensive. They are more accurate, so if you need a really accurate sine or cosine function, then you probably still want to call the accurate version, but a lot of this is about getting essentially close enough to be useful, which will depend on what you are using it for. But this is a pretty nice approximation. Just to be clear, this is a half cycle, so this is really only from sort of -1 to +1, half cycle sine wave, but with a fifth order polynomial that's 4 multiplies and then 2 FMAs, which is fused multiply add, basically the processor doing an add and a multiply together in one instruction. So yeah, six instructions gets you pretty close to a usable sine wave. So this is what we're doing. Again, we've got we've got the instruction set to exploit the data level parallelism. We've got the interleaving of operations to exploit the instruction level parallelism, the processor's ability to fire off multiple instructions at once. And we are basically trying to decouple the algorithm design from the instruction set, from the decisions about interleaving, and then we can choose whichever version of this actually delivers the best performance on the CPU we're running on, and maximize the use of its resources. And we can even do that at runtime. So you can actually run micro benchmarks on some of this stuff at runtime if you don't know what kind of machine you are running on, and just pick whichever code path actually is most efficient on that particular hardware, because there are, particularly with Intel and AMD, there are some quite big differences between generations there. All right, about halfway through and we haven't seen any oscillators yet. Let's make an oscillator. So that's our naive sawtooth wave. It's got a branch in it, so it can't work with these vectors because a branch is requiring each lane to potentially go down a different code path, and we can't do that. So instead, I'm going to rewrite it branch free, essentially just like this. So there's a single pick instruction there, which is comparing the waveform to the reset threshold, and then if it's not past the threshold, it just phase increments it, and if it's over the threshold, we've actually pre-computed essentially -1 plus the phase increment, so we can add that back on in one operation, and that will give us a branchless parallel naive sawtooth. So what happens when we actually compile that? So if we do it at 1 times 1x interleaving, so that's like one stream of instructions, 4 data lanes, it's basically giving us a 7 instruction inner loop. That's pretty small already, pretty efficient, sort of 1 3/4 instructions per lane of data. If we interleave it more, so that's at 2 times, it will be even slightly more efficient. You know, it's slightly more code, but it's processing twice as much data for less than twice the cost. So we're gaining efficiency there. And as we go up to 4x, we can see it gets better again, because we're essentially spreading the cost of the flow control across multiple lanes and only paying that penalty once. So how does it look? How does it perform? Well, pretty nicely. We get a 22-fold speed up. So this is basically instantiating the same code at different widths, trying them out, and we can see the most efficient is is 12 instruction streams, so that's 48 wide, and that is 22 times faster than the scalar naive sawtooth. There's only one problem with this. This oscillator sucks. I would play you audio of this, but there's actually a rule in the Geneva Convention that says you can't play naive sawtooths to hungover DSP developers at 9:30 in the morning. It's not fair, and it's not right. So it's just, you might find uses for this oscillator, but I mean, I can hear that aliasing just looking at that. That's the frequency it's actually supposed to be producing, and then this is all the crap. So it's not a very nice oscillator. Also, why is it only 22 times faster? Shouldn't it be faster again than that? Well, there's a couple of reasons for that. And the first is that in this particular algorithm, because there's not really that much in the way of dependencies from one cycle to the next, the processor can actually start working on the second iteration of the loop before the first one's completed. So this is sort of a bit more efficient than it might look, which means there's less room for this one to become more efficient. But the other thing you can see is we start getting these little stores, and somewhere there's some loads creeping in, and that's literally just because we are running out of machine registers. With that sort of 2.5 registers per stream, it's not enough. So there you're getting what's called spills and refills, where basically the processor is saying, I need to assign a variable to a register, but I'm out of registers, so the compiler is generating loads and stores to basically evict machine registers back to cache or back to memory, and then reload them when it needs them again, and you start to lose efficiency, and we'll see sort of some of the consequences of that a bit later on. But still, it's a decent speed up. If we go to sort of 8 wide, it's 18 times faster than scalar. If we go to 12 wide, it's 22x faster. But it's still just not a very nice oscillator. So let's try and make something a bit more interesting. So we can do a triangle wave. Now, this is still a naive waveform, but naive triangles are not as horrible as naive sawtooths. So it's using this triangle formula, which is basically subtracting, essentially subtracting the top and tail of the phasor waveform, and that gives you a triangle. We can write it in code like this. So it's taking the absolute, and it's then picking and flipping the basically flipping the negative side of the waveform, so that then gets added instead of subtracted, and it gives you a triangle wave anyway. And at sort of high levels of interleaving there, I mean, it's a bit hard to see the numbers there, but it's still 9 times faster than the naive scalar sawtooth. It's still not a great waveform. Like I said, there's still some aliasing on this, but this is a useful foundation for doing band-limited waveforms with some simple polynomials. So we'll take that sine polynomial approximation. It's a half-cycle sine wave, so we can just plug the triangle directly into that, and we'll get a symmetric sine wave out of that. It's 5 or 6 multiplies, an add and a subtraction, and it's pretty good. This isn't a perfect sine wave. It's an approximation. So there are some additional harmonics, but basically almost all of the error from an ideal sine wave is in these first 4 harmonics, and even there we're talking at sort of -50, -60 dB. So although I wouldn't necessarily use this for example, calculating filter coefficients, sort of as an audio sine wave, it's actually pretty damn good, because any of the noise is sort of harmonic a little bit of harmonic distortion at kind of, like I say, minus 50 dB, sort of first and second harmonic. And it's still a lot faster than that horrible naive sawtooth, which is the cheapest and most basic oscillator you can have. So this is the code when it's compiled. This is just the single interleaved variant, but just to show that it's kind of completely clean. There's no branches. There's no switching around. It just runs straight through. You can stack this up nicely with interleaving. And then this is basically how much more efficient it is than the scalar naive sawtooth, and it's basically 5 or 6 times faster. So we're talking very, very inexpensive waveform generation still, and that's quite a nice sine wave. So then I thought I'd try a quadrature oscillator, and this is another way of producing sine waves. It also gives you the cosine for free. It's inherently a branchless algorithm. It's a sort of iterative thing using rotation. So it should be quite nice. There's a couple of problems with it, which is firstly the coefficients are a bit more costly to calculate, and because it's iterative, essentially you can run into problems with numerical instability. So if you try and, for example, FM one of these, they have a little bit of a tendency to blow up. The other issue you run into with this one is there are quite a lot of data dependencies in it. So it's using a lot of multiplies that then don't produce a result for a number of cycles, and it needs 5 registers per lane. Essentially what happens is we run out of registers before we can fully stuff the CPU with work, and this is just because these multiplier accumulates take 4 cycles. There are 4 we can send at once, but then we need to find another 3 cycles of work for the CPU to usefully do, and we just run out. There aren't enough registers on this M1. So, comparison of the performance we get with these, we can see that the polynomial is ahead. I mean, they're both quick. You know, we're still, again, even the Quadrature is more than 3 times faster than the crappiest oscillator available. So you know, it's not doing too bad. It's very high fidelity. It's simple, and you get a cosine wave for free as well. So it might be quite nice for LFOs and that kind of thing, where you want multiple waveforms. The polynomial is more performant. It's numerically stable and doesn't require calculation of any expensive coefficients. But let's try and do something a bit more ambitious, which is a variation on the polyblap. So this is polynomial bandlimited steps. Those of you who saw Geraint's talk yesterday, he's doing some very, very clever stuff with this. This is a much dumber version of the polyblap, but just to show you how you might go about implementing it branchlessly and sort of whether that works out. So what we're going to do, we generate the naive sawtooth, and then we correct the step function to try and remove as much of the aliasing as possible while keeping as much of the harmonics as possible using a polynomial. And this is good for sort of sawtooth triangles, square waves, PWM, and hard sync. So a lot of the classic analog waveforms, it basically works pretty nicely. And the traditional polyblep uses look ahead to detect when a branch is coming up, when a phase reset is coming up. We're not doing that here. So instead, what we're doing is basically windowing the naive waveform, and we get something that's sort of look ahead free. We don't have to explicitly look ahead. At the same time, if you were to kind of do something to this waveform while it was resetting, that would give you some problems. That would give you essentially a bit of sort of error in that transition shape. So it's, I would say, partly look ahead free, but if you're just running sawtooth waves, then it's not a problem either way. It stands up okay under frequency modulation, and you can get this to do hard sync, although it is more complicated to do that. And so it's really just generating these two windowed quadratics just to smooth off the transition there. So this is what the code looks like, and we're doing a sawtooth and a square wave, generating windows around the essentially the high to low transition for both waveforms, and the low to high that the square wave also needs. Square wave has the two transitions that both need to be corrected, and then summing that all together. Again, nice, clean, linear code, very performant, and we're getting sort of 4 or 5 of these anti-aliased-ish, we'll come to that in a minute, saw and square waves for the price of one naive sawtooth, which is kind of nice. But we're just using this very basic quadratic polynomial to try and correct the error between a bandlimited and the ideal, the naive and the bandlimited waveform. And as a result, we have a pretty, like, the top end of this is a lot better than the naive waveform. Like, you could tolerably listen to this if you're not very fussy, but it rolls off too much here, and there's quite a lot of aliasing still there, but it's dropping off a lot faster than the naive, at least. And better polynomials may be available. This is actually an area that I need to do a bit more research on to figure out whether I can get a better approximation to that transition using a higher order, like a third or a fifth order polynomial, which would, again, get a steeper roll-off on these unwanted harmonics. But at 2x oversampling, it's actually getting, we can't see this very well, but I sort of would consider this a Gen X and Boomer acceptable waveform. Is gonna, your dad will like it, your dog will hate it, basically. There's still quite a lot of kind of muck here above 10 kilohertz, but within the range that human hearing is sort of sensitive to pitch, it's actually pretty good. By the time you go to 4x, even above 10K, it's still at minus 78, which I think if you're doing a kind of an analog synth, which is going to have a lot of self noise anyway, that's going to be kind of within the noise floor. And this is all still for the price of one naive waveform at a 1x, and like I say, with better polynomials, you could get better results again. So that's a quick tour of what I've been working on. What can we see? This branch-free and parallel code, you can get quite a big efficiency gain. You can use this for other things besides oscillators as well. It works really, really nicely for filters, so you can get huge speed ups on filter code with this. You can build pretty much anything that doesn't have a lot of memory accesses. Anything you might want to build in a synthesizer, you can build with this sort of approach and get these large speed ups. Envelopes are kind of fiddly, but they can be done. The visible register file sort of limits the maximum level of efficiency we can get. These processors, they actually have more registers available under the hood, and they rename things to them, but you can't actually get at them. I'm kind of hoping that ARM's SVE2 instructions might help a bit with that, like basically by treating those 428-bit units as one 512-bit unit, so you only actually need one kind of named register to dispatch sort of 16 lanes instead of having to do 4 times 4. We'll see. That's not available on any kind of consumer hardware yet. And just beware of compilers with good intentions, and always be profiling. Thank you.